Hello, welcome to the Heuristic Algorithms class. And in this first video we're going to discuss the extent of what heuristic algorithms are and how we will use them in this course and in practical matters, and what is needed to learn about heuristic algorithms. In order to understand what heuristic algorithms are, I created this conceptual map, and as you can see, I have some color code in it. Let's see, we have first we can discuss problem theory, and this problem theory tells about the most typical problems that in operations research are studied. These problems facilitate or are relatively frequently found in more practical problems, of course embellished or in a way more sophisticated due to the real constraints. And you have, for example, the traveling salesman problem, in which a vendor needs to visit a set of cities one at a time without coming back to the same city, and making a circuit coming back to the original city in which he or she started. We have a knapsack problem. The knapsack problem is a problem in which you have to put a variety of items inside the knapsack. Each one of those items provide a specific benefit, but all of them, each one of them occupy either a space or carry some weight, and there is a limitation on the space or weight or both that need to be accounted in. And these type of problems, as you can imagine, appear again and again in settings like logistics. And there are other problems like set packing or set covering, and in the scope of this video I'm not going to go into the details of that, but you have these conceptual problems, and we're going to use some of these problems to test some of the algorithms that we're going to have. Now, in other courses like operations research, you have a mathematical programming. You learn about the simplex, linear programming or nonlinear programming, or even integer programming, or mixed integer programming. And all these tools allow you to, through, for instance, branch and bound, to obtain the optimal solution. The problem is that these algorithms achieve the optimal solution after a long run, and sometimes it's better to have a fast approximation rather than a very slow, precise solution. And that's when the algorithms come into practice. Basically, when we have combinatorial problems especially, we would like to use some algorithms that allow us to converge faster to a good solution, even though sometimes it's impossible to know if we obtain the optimal solution. But in general, it would be better than just a random or a common sense short solution, because we can, with the help of the computer, explore faster the solution space. So in order to implement these heuristics, we will need some knowledge of computer programming. There are several things that are applied when we are using heuristic algorithms in practice. We can use a variety of programming languages, which you could include C++, or Java, or JavaScript, Python, or Visual Basic. In our course, most of my examples will include Visual Basic because it's relatively easy to use, fast to compile, and everybody has access to it. As long as you have access to Excel, most of us have access to Excel. Additionally, we would need to represent the information associated to our problem. Usually we do this with databases, and in some cases spreadsheets could work as databases from which we read the data of our problem, and we can write down into a database also the answers in order to further later represent these solutions in a more user-friendly than just a flat file. So we would like to have access to those spreadsheets and databases, and we have off-the-shelf software that can that usually is implemented or it's implemented mathematical programming in such a way that most mathematical programming programs are already out there ready to be used. So in most of the cases, nobody would actually make or write its own linear programming solver. It's easier just to pass the parameters to a solver and let the solver do that part of the job for us. So we can actually have some kind of a mixed solution in which if the linear programming is or the standard mathematical programming is a faster and more accurate solution, we can just pass the parameters to that part of the program and then solve the rest of it. And that brings us to our meta heuristics. We have heuristics. Heuristics are algorithms that we use with some general knowledge, and it usually works. And it could be anything in the field of psychology. A heuristic is just, for instance, how much salt you put into your soup. Maybe you shake the salt on top of the soup maybe 2 times, because 3 is too much and 1 is not enough. So that would be just a very simple heuristic right there. This is common sense logic. We're going to try to achieve a better or more sophisticated algorithms than just that. And we call them meta heuristics here because these heuristics apply to many problems. So by using the same methodology, for instance genetic algorithms, we can apply the same logic associated to in genetic algorithms to solve a variety of problems, which could include things as diverse as designing airplane wing, or scheduling a crew, or defining the optimal way to cut material to reduce the waste associated with cutting such material, etc. And we have these algorithms. In this example, in this graph, I am mentioning simulated annealing, genetic algorithms, and tuple search, but they are not by far an extensive list. So this is just a few examples. So real-life combinatorial problems motivate the understanding of the problem theory, and it also motivates the generation of more meta-heuristics. These meta-heuristics are implemented in computing by using computing tools, and just as mathematical programming is implemented in off-the-shelf software. And that's pretty much it. This is the map. We're going to learn about all these topics in this course. I know it might sound like a lot, but we're gonna explore all these topics little by little, and I hope you will find them interesting.